Assalamualaikum and good day. In the previous chapters, we had learned about various unit operations that involve various phases, for example, solid, liquid, and gases. In most of the problem that you came across previously, the description is very straightforward. You do not have to estimate or measure the physical property of the given chemical species, be it solid, liquid, or gases. In this chapter, we will discuss about estimating physical properties using various resources and use the information to solve for complex materials balance problem. At the end of this module, you will be able to explain the methods to define and determine values of physical properties for liquid, use resources available to get information on physical properties of substances, and estimate the average density of liquid using various estimation methods. As you will come to discover, problems in process analysis are rarely so conveniently self-contained. Before you can carry out a complete material balance on a process, you usually must determine various physical properties of the process materials and use these properties to derive additional relations among the system variables. The typical physical properties that engineers are interested in include density, vapor pressure, solubility, heat capacity. Usually, these physical properties can be measured. The easier way to find their values are based on the reported values that are reflected from your previous exercise in Chapter 2, where you get all the information from handbooks, journals, or any other technical publication. Since there are always variations, either in the form of chemical atoms or species or the operating condition, the actual physical property values of a system cannot be fully obtained. A suitable estimation approach will provide us with estimates on the physical properties of the chemicals in a specific system when there is no data available. We can then further extrapolate them to the conditions we are working with. When there is no data available or when you require a much higher precision, the next resources available is just to measure the physical properties by yourself via an experiment. You can refer the method to conduct this experiment from any physical, organic, or analytical chemistry handbooks or guides, or even from technical publication. When you heat a liquid or a solid, it normally expands, which means its density decreases. In most process applications, however, it can be assumed with little error that solid and liquid densities are independent of temperature. Similarly, changes in pressure do not cause significant changes in liquid or solid densities. These substances are therefore termed incompressible. Since engineers are going to deal with various liquids mixture, so how would you actually estimate the liquid density of two different liquids with two different densities? We are going to explore this problem in this module. Table B1 in our textbook shows a physical property data of various substances or chemical species available. The density of the chemical species can be determined based on the SG value shown here. Paris Chemical Engineer's Handbook also lists densities of liquid water and mercury at different temperatures and gives expression on page 2134 through 2136 that may be used to calculate densities for many other substances at different temperature. Pauling-Prosnitz and O'Connell present a number of methods to estimate the density of a liquid for which tabulated values are not available. Some of these estimation formulas are also given in Paris Chemical Engineer's Handbook. Let's try this one. We are going to actually estimate the density of a liquid. Here you are given 37 wet% of aqueous solution of nitric acid and you are required to find the density of the mixture. Using Paris Handbook, you can actually find by putting a search on HNO3 or nitric acid, and it will give you the reflective page that have information on nitric acid. Here, the page is 2107. Next, we are going to refer to page 2107, where the horizontal values are the effect of temperature and the vertical values are the effect of the composition of nitric acid in the solution. The point of interest that we are looking at is at 20 degrees Celsius, which is at room temperature, and 37% of nitric acid. So the estimated density of nitric acid using Paris Handbook is about 1.2270 kilogram per meter cube. To start with the estimates for 37% nitric acid concentration, we have to find what is the density of water at 20 degrees Celsius. Here, the density of water is 0.998 gram per centimeter cube, and the density of a commercially available nitric acid at 20 degrees Celsius is about 1.502 gram per centimeter cube. There are two ways for us to estimate the density of liquid. This applies for a temperature range from 0 degrees Celsius to 100 degrees Celsius. The first estimate is based on what we call as a volume additivity technique. Here, the average density is just the inverse of fraction divided by the density of pure component. The second estimation technique is known as the average pure density, in which the density of solution is estimated based on that of pure component multiplied by the mass fraction. Taking the two values found from the handbook as the true value, then the estimation error for 37% nitric acid was found 6.9% and 3.2% respectively. Let's look further on the difference of these two density estimates. What we have here is the actual data from experiment for sulfuric water and methanol water mixtures. When we use the method volume additivity and average density, we can see that the estimates is a little bit deviates from the experimental data for a sulfuric water mixture, whereas for methanol water mixture, where they are very miscible to each other, the average density and the volume additivity gives a very good representations of the density of the mixture. This ends the module. Please refer to the next module on ideal gas.